So happy Tuesday, everybody. Did anybody miss the last lecture and would like a copy of the notes from the last lecture? Okay, that's good that nobody missed the last lecture. So these are the notes from today's lecture. Are there any questions before we get started on the exciting content that we all are eager to find out about since discovering the software crisis last time? Okay, if there are no questions or comments, we will jump right in. By the way, this term objects was coined by a student that took this class. So just to give a little context to what we're going to talk about today, these are the different major topics in the software engineering lifecycle. It starts with a problem or a challenge, right? Some problem we want to solve or a challenge we're given. And then we formulate a requirement specification. In terms of your degree, this is usually just given to you in terms of your master's degree or bachelor's degree or whatever degree you're taking. So it might just be given to you in industry too. Then there's the design, and this is what we're going to be talking about a lot over the next few weeks. The design. The implementation is what you learn in your programming, Java programming modules, or that's what the focus is, let's say. We are going to talk about it in this module, but the focus is in the Java module. And there is another module that's all about testing that you can take if you're interested, with Marcus Rogenbach. And I've added the other thing, maintenance. So that's something that a lot of people don't talk about, but there are these, they're all very important, right? And actually maintenance is, now it's more than 50% of the cost of any software project, right? We didn't hand those out yet.
Oh yeah, that's
Where are the lecture? Okay. So maintenance is really huge. Everybody knows that, right? Because every day you're downloading gigabytes worth of software updates, right? That's all about maintenance. And your first job, by the way, if you go into industry as a developer, your first job will be maintenance. And another background note, these slides and notes are mostly derived from this book, Designing Object-Oriented Software by Worf Sprock et al. Right? And they did write a follow-up book, Object Design Roles, Responsibilities, and Collaborations. And don't be afraid to look at these books if you're not understanding what we're talking about in the module. I remember, like I said, as being a student in this module, and just having this feeling like, wow, I'm not sure I understood everything that we went over in the lecture today. I'm going to read the book. So there's a corresponding book chapter for each lecture. And it was fun. I really enjoyed it. I guess I'm just strange that way. But I like understanding all the topics. I enjoy that. So software design is all about abstraction. How do we take something that's as complicated as a piece of software and make it more abstract, or come up with more abstract representations of that software? That's very, very important, right? So that's where we're going to start. Abstraction is a so-called mental model. Its abstraction in a mental model must simplify the real world or the software, otherwise it won't help. Right? You experience that every day. How often do you think of something and then you go to do that thing and you find out, oh, this is more complicated than I thought it was. Right? It happens to me almost every day. Right? So we build mental models of the world, and the mental models of the world are simpler. They're an abstraction of the real world. So we are going to build software models. That's what software design is about. Simplifying the software, building a model of it, and we hide the details so we don't need to understand how the system works. We just concentrate on what it does. And I'm going to say that multiple times over the next few weeks. We're focusing on what the software does, not how it does it. That's our starting point. So we decompose the system into parts, and later on, during the implementation phase, you can look inside, right, and find out how it's going to work. But the design is all about what is going to happen. And just in case you're wondering, if you look up the word model in the dictionary, this definition is a standard or example for imitation or comparison. A representation, generally in miniature, to show construction or appearance of something. Right? So we're building a model of the software. Right? Before we build the Empire State Building, we construct a model of the building, right? And it's probably, the first model is very small. Maybe we make another model that's bigger, and we make another model that's bigger, and so on, before we build the real thing. A short note on the evolution of software abstraction. So when software engineering started as a discipline, the abstraction was focused around processes. So you can think of that as a control abstraction or a process-oriented abstraction. And this is the way we naturally tend to think as people. I don't know what the reason is, but this is generally the way we think as people. The early stages of design are driven by how things work. And I like to use the analogy of a process-driven abstraction as like an assembly line. You know, when you're building something on an assembly line, it starts at the beginning of the assembly line, it moves down the line, and then there are some operations or processes performed on that object, like building a TV. So the first part is added, then it moves down the assembly line, the next part is added, it moves down the assembly line, the next part is added. That's a process-oriented abstraction. It's also like a finite state machine. And this is how software design, this is the kind of model that software design used to follow, process-oriented. But we're introducing something that might be new to you in this class, maybe. And it's a data-oriented design or a data-oriented organization of software. So instead of thinking about what happens in the order in which it happens and how it happens, like an assembly line, we're going to think about data. Where is the data stored? How is the data stored? And how do we organize the data in the software? So it's a data-centered view of the software. The other terminology for that is called object-oriented design. So you've all heard that term before. Object-oriented methodology, object-oriented design. What does that mean? It's a data-centered view of software. It's all about where the data is stored, and how we access the data, and where the processes that operate on the data are stored or organized. So for data abstraction, we hide the implementation details and we focus on what a data type does, but not how it does it. The how is in the background somewhere. It's you know that someday you have to think about how things work, but not today. Not this semester, actually. Next semester you can think about how things work. When you get that coursework that says, okay, please implement this piece of software, you can start thinking about the how. For now, we're just thinking about what. So object-oriented design, or object-oriented design as some students used to call it, we always focus on what the system is supposed to do, what the software is supposed to do, not how. This is for the design process. The implementation is the how, the design is the what. So I'm going to repeat that often because it's very important. So we start out with a requirement specification, and step one is to identify the objects that we need to carry out these requirements, to fulfill these requirements, right? We identify objects the system will need to carry out whatever the requirements are. Then we identify operations to be performed, and we identify the information needed. Today, we're talking all about this second point here, identifying objects the system needs to perform to carry out the requirement specification. The next step is assigning responsibilities for the operations and information to objects. So we have a special lecture just on this topic, which is next week, actually. Each object knows how to perform its own operations, and each object remembers its own information, right? So each object stores some data, and it stores the methods that operate on that data. So it's, again, this data-centered organization or data-centered design. What is an object? So this is a good test question, by the way. What is an object? This is also, one of the things I like about this module is this is also a good job interview question. So when you're sitting in a job interview, you could get this question to somebody on the other side of the desk, because you always have tests when you apply for jobs in software. Does anybody know why you have tests when you apply for jobs in software? You often have to pass a test. Anybody ever have a job in software as a software engineer, apply for a job like that? So if you apply for a job as a software engineer at, say, Google or Microsoft, Facebook, or some big company, some famous company, they will give you a test before they give you the job, and you have to pass the test. And this could be a test question. What's an object? What would you say an object is? And they have to do that because they get thousands and thousands of applications, right? And they have to make sure that the people who are applying what's written on paper is corresponding to the actual person and what's inside their mind. So an object knows what it is, it stores its own data, in other words. It knows its responsibilities, in other words, it has all the methods that it needs to process the data. And it knows it has tasks that other objects can request on that data, right? Some operations. It has a role to play in the system and knows how to do it. And it doesn't know how to do anything else. Right? This is called information hiding, right? So the whole idea behind object-oriented methodology, one of the main principles is information hiding. You can think of other analogies. I'll use a lot of analogies during this software design. You can think of your phone, right, as an object. It's a very complicated object now, but it knows how. All you see is like the button to unlock the screen. Maybe you press the phone button and then you press the call button. Nobody does that anymore. Imagine you had a normal phone. So, but all the complexity of how it works is hidden, right? If you had to know how your phone works, that would be bad. That would be bad because you would never make a phone call again. But the complexity is hidden, and that's what this term refers to, right? Information hiding. Encapsulation is also another important term used in object-oriented methodology, and it could also very well come up in a test or a job interview. So encapsulation is grouping data and the operations into a single object, right? So every object will store data, right? The phone stores a lot of data now, 64 gigabytes of data. And it hides the data and the implementation from the rest of the system. So I can't see how this phone works. I can only see the methods, the public methods that operate on the data, and that's it. I can only see sort of the input and the output. That's the public interface, the public part of the object, what it can do. I know what the phone theoretically can do. A better or simpler analogy is a DVD player, or an old-fashioned DVD player with the play button and the rewind button and the fast-forward button. You know what the DVD player does. The parts, those buttons that you can see are the public part of the object. And then everything underneath the plastic cover is the private part, how it's done. If you had to know how the DVD player works, you'd also be in trouble, right? Because it's very complicated. But that's encapsulation. That's a literal analogy of encapsulation. That plastic case or the metal case that surrounds the DVD player, it encapsulates the private part of the DVD player. And that's going to be a recurring theme, by the way, in the software design. So back to the software lifecycle, we have the requirement specification, what the software can do, what its limits are, and the importance of each feature. From that text document, you have to derive some sort of software design. That could also be called the software engineering specification. There's lots of construction going on these days. Exactly during the lecture. Maybe I should close that. Was it a jackhammer last week? I remember hearing a jackhammer during one of the. So the design, we find out how to come up with a list of objects that fulfill the requirements, and we then derive the public behavior of those objects. Right, the public methods, the methods that we can see from the outside of the object. And we investigate the patterns of communication between the objects too. This is all part of the software design process. And that's this semester, by the way. We're going to look at these three stages. This is part of the design. The implementation, we look at next semester, and Tom's going to lead us on that. And then the final stage is the integration and testing and maintenance. Here's what that looks like as a figure. It's an iterative process. The time is, the start point is at the origin, and time is mapped in a cyclical clockwise fashion. So we start here, and the first stage is the requirement specification. There's a short requirement specification phase. Then there's a design phase. There's an implementation phase, a testing phase, and it goes back into the requirement specification phase. So it's an iterative process. And then it goes back into the design phase, implementation, testing. So that's the software development lifecycle, the way it really, a good software development lifecycle, a good one. This one is not so good. It starts out with a verbal requirement specification, never written down at all. It goes into implementation, and then it continues into implementation, and it continues into implementation. There might be some testing, and then it goes back to the verbal requirement specification. This is another software lifecycle, by the way. This does happen, but this project is going to fail. This is the failing project development lifecycle. This is the one that's going to succeed, and this is the one that's going to fail. So one of the major goals is software reuse. So we want to write software that we can reuse over and over again. This is one of the advantages of object-oriented design. Because once we define an object, we can use it in any system, anywhere, anytime. Does anybody know where you've seen that already? Has anybody seen this already? Where's an example that we can actually see this in action?
Is it what they call inheritance? Also.
Inheritance, yes, that's true. That's true,
If
yes.
I've got one type of bank account and a software that runs that bank account, I introduce a new style of account. Without having to rewrite the entire set of software, I can inherit.
That's correct.
And is polymorphism another strand to it?
It is. How about something more concrete, though, that you personally can see on a daily basis? You can see this in action, and you have seen it. You're actually using it. Who's taking the Java programming class? Everybody, right? So the Java library is an example. The Java library is an example of actually everything we talk about in this module, right? So the Java library is a set of objects, right? And you're using those objects every time you write a Java program. And you're using them and reusing them and reusing them over and over again, right? So it's pretty handy, right? It's kind of nice, very useful. So a major goal of good software design is reusable software. So Java is object-oriented, and it's a data-centered design, like we've been talking about. And the goal is to design reusable components, just like in the Java library, right? We want to build an application that meets the specifications, right? So we want to build something that's maintainable and extendable. And at the same time, we want something that's reusable, right? So we want to have reusable components, right? Objects that can be reused over and over again. So the ideal application is a framework implemented with components or a set of objects that you can use over and over again, just like in your Java programming exercises. So we already looked at encapsulation, information hiding, and we're going to talk about some other terms, some other important concepts. Here's some more about encapsulation. So encapsulation, we place the related data and information and functionality into one object, right? This is sort of what it could look like if we would try to draw it. Data and operations. We decide which functions or methods might be needed by other objects, and that becomes the public part of the object. Everything else is hidden. So a trivial example might be an object called time, right? Java has an object called time, right? And it has to store the current time, right? And the current date. So it will define a public part, which is a method called getTime, right? And then it has a private part that you can't see. You don't know how the Java time object actually works, right? You just know there's a method called getTime where you can get the current time, right? You don't know how that data is stored, where the data comes from, and so on. Probably it comes from the operating system, probably. So that every object is divided into the public and private parts, and that's what encapsulation is about. And you also mentioned polymorphism, so somebody also, what's your name, by the way?
John.
John. John also mentioned polymorphism already. Another word for this is overloading, by the way. So a lot of people have heard the term overloading. Polymorphism, by the way, is definitely it could be a test question or a job interview question. Like it's definitely possible that you could be sitting at a job interview and somebody asks you, what do you think polymorphism is? So the idea is to allow the same method name to access different functions in different objects, but the name should be the same logical function. So different objects can respond to the same message or the same function, for example, to print, or to display, or to test. Does everybody know one of the methods that every object can respond to in Java? I'm sure you've seen it before, and it's in your Java programming module. That's a good question, good quiz question. There's a method that every Java object can respond to.
Constructor.
A constructor, but the constructor is always changing depending on the name of the object, right? But you're right, the constructor is always there, but there's one example of a method. It's got the same name in every object, and every object can respond to it. So it's sort of a classic example of polymorphism. Any Java experts or something like that in here? It's called toString. So every object in Java defines the toString operator, right? And that prints out the name of the object. Right? If you didn't know that, it's very good to know. It's very useful to know. So different methods with the same name but different parameters are also possible. So in Java, every object has a toString method, right? That's a good classic example of polymorphism. But what that method returns is different for every object. The name and the input is the same, but the value it returns and the implementation is different for every object. So different methods with the same name but different parameters are possible, like print or print with a file descriptor. But the idea is the user has one conceptual action and one logical call, right? And the objects know how to respond to that method. They know how to print themselves or to formulate themselves into a string, for example, or display themselves and so on. Here's a fun one. I still remember learning this and not actually understanding it the first time I ever saw it when I was a student. Classes and instances. I like this topic. And this is confusing in Java, by the way. This is confusing when you first see it. So often a system needs many copies of a given kind of object. So there's a need to organize the objects of the same type. So if we were designing a car, we might have a tire object or a wheel object. So you have a description of a wheel, but you need 4 of them. The 4 wheels that you create are instances of the wheel object. It sounds kind of funny because it sounds like I'm saying real, but not pronouncing the R, wheel. Anyways, so that's the difference between a class and an instance of the class. So you define classes and then you create instances of them. And you're always doing this in Java. You might not notice it because Java doesn't make it very obvious that you're doing it sometimes. So a class is a set of objects that share the same behavior. It's a generic specification of all such objects and a template that defines all the objects. And then an instance is a member of a class or the object itself. So you create instances of a class. So somewhere, if you're building a car, there's a description of a wheel. Just the description, that's a class. That corresponds to class in this example. When you actually build the wheel and you make 4 of them, those are the instances of the wheel. And you have to know the difference between these 2 things if you want to understand what's happening in the software.
So a class is a description, and then an instance is a copy of the object.
Yes, that's right.
I'm struggling to see the difference between object and class.
That's right. That's what we're talking about right now. That's what this discussion is. So if you want, in Java makes it confusing because it lets you access static classes where you don't create an instance of them and you have a static copy or a dynamic copy or a dynamic instance. So these 2 things often get confused in Java. It's very easy to get them confused. And we're going to go over examples of this, by the way. You can find examples of this. There are examples already on Blackboard, and that we're going to go over in this class. No pun intended. But you create an instance of an object whenever you use the word new, or whenever you construct an object. Right? You create a new instance of that object. I hope that makes sense. It will make sense eventually as we go over examples. It will make sense. So inheritance is another important concept for the object-oriented design. So this is very closely related to software reuse, as John pointed out earlier. It's a principle that lets us maximize software reuse. So often objects that are similar but not identical have shared behavior. So an object A, here's an object A, can do X. It can carry out some function. Object B can also carry out that function, but it can carry out an additional function. So rather than duplicating the so-called shared behavior of X, we inherit the shared behavior of X from A, right? So we define a new object called B, and it adds the functionality Y, but it also inherits the functionality X. We call B a derived class of A or a subclass of A. A is the base class or superclass. So base class or superclass. In this module, actually, the terms I usually use are parent and child. I think this makes is the most intuitive. Plus, we're talking about inheritance, right? We inherit from our parents. So in this instance, A is the parent and B is the child class. And that's usually how we're going to refer to that. But different programming languages use different terminology. C++ uses a different terminology to Java and so on. But it depends. In this module, it's usually going to be parent and child. And I think you've all seen this already, maybe. A little bit more on terminology, just to confuse you as much as possible. The Java uses the term superclasses. Subclass C++ uses base class and derived class. And we're going to use parent and child class. I just think that's the most intuitive. And we're not going to talk about this. We're going to skip this bit because it's very, very confusing. Abstract versus concrete classes. This is something you probably haven't seen yet in your Java programming. Does anybody recall seeing this in the Java programming module? Probably you haven't seen this yet. So you're going to see it, by the way. It's going to come up very soon. So you're going to see it twice. Sometimes it's convenient to define classes that have no instances. In other words, we never create them. And it allows for a kind of abstraction to a higher level class, right? Abstract classes are fully specified, though not necessarily fully implemented. So a menu class may have a display method defined but never implemented. So menu is, in this case, it's an abstract class, and it has a method called execute. But when you call menu execute, nothing happens. And then from the menu, the abstract menu class, we derive two concrete classes. These are classes we actually create instances of. Like, for example, text menu or button menu. So this is an abstract class. These are concrete classes. We can instantiate text menu and we can instantiate button menu. And when we call the execute method on these classes, something actually happens. Like the execute method is implemented and something happens. Right? The menus, the text menu and the buttons menus actually respond. In Java, abstract classes are not called abstract classes. Does anybody know what they're called in Java? Abstract classes are not called abstract classes in Java. They have a different name. No Java experts in here. They're called interfaces in Java. So you might want to make a note of that. So if you're trying to find out more about this, you want to understand it better, you can look for Java interfaces. Here's an example of a class hierarchy. So we have this object called figure, and this is a drawing. We often use this, refer to this drawing editor, this fictitious application. Has anybody here ever drawn a diagram with software, using a piece of software? So one person has. Anybody else ever draw a diagram before? Two people. So that's what we're talking about here, a drawing editor, a program that you can draw things in, like a square or a line or a circle or something like that. So we have an object called figure, and it has three methods: draw, area, and location. And from that object, we have two derived classes or child classes. One's called a polygon, and one's called a circle. And they also have draw defined and area defined. Draw and area. But they have something else too. They have additional information. The polygon has a set of vertices, and the circle has a radius. So draw and area, that's an example of polymorphism, right? So a polygon is going to know how to draw itself, and a circle is going to know how to draw itself. A polygon is going to know how to compute its own area, and a circle is going to know how to compute its own area. But the information the polygon needs is different. It needs a set of vertices. The circle needs the radius and the center point. And then a square is a special kind of polygon. And the draw method, look, it doesn't even have its own draw method. It uses the same draw method as the polygon, but it defines a different area method. It could use the same area method as the polygon, actually, but it's decided to have its own implementation of area, which is quicker, it's faster to compute the area of a square than an arbitrary polygon. And then it has an additional attribute just called side, one side of the cube, right? So each of the child classes inherits behavior from its parent classes, and it adds some additional behavior, and it may redefine some of the functionality of the parent. That's a sample, a typical class hierarchy. So those are some preliminary terms that we're going to need to understand the rest of the software design. So we have three major phases in the design. We have an initial exploration phase, where we identify classes, operations, and collaborations. Then we have a detailed analysis, which includes building class hierarchies and subsystem identification. And we're actually going to go through each one of these phases in the forthcoming weeks. So find classes, finding operations, also called responsibilities, finding collaborations, that means the communication pattern between objects, building class hierarchies like we just saw on the previous slide, and then identifying subsystems, which we have not talked about yet. And this is generally an iterative process. It's not like the waterfall model where you just start at one point and you finish at the end. It's circular. So you're always identifying classes, you're always identifying operations and responsibilities and collaborations iteratively. So this is a starting point. This is your first procedure. The first step in the software design. Put a star on this slide because it's really important. So guidelines for identifying objects or objects. Given a specification, a class or an object corresponds to a noun. Everybody know what a noun is? Does anybody remember the definition of a noun from their school days? I still remember the definition of a noun that I learned as a child. I don't know why. Maybe because they said it over and over again. Nobody remembers what a noun is from their old school days? Nobody? Well, you're going to have to find out. You're going to have to know what a noun is in order to do the first assignment and the first exercise. So a noun, in my school, we were taught a noun is a person, place, or thing. Is that what you guys learned? Anyway, you'll have to know what a noun is if you want to succeed. Step 2 is to use singular nouns by default for all of your objects. So vertex is an example, right? But you generally wouldn't use the word vertices as a class. You would not use that. Methods correspond to verbs. For example, vertex draw. If there are only 2 things you remember from this module, it's those rules 1 and 2. Classes correspond to nouns, and methods correspond to verbs. This is one of the ways I identified a failing project, by the way, at my last job. So I saw the source code, and I could see that their classes did not correspond to nouns. And I knew it was a failing project as soon as I saw that. Methods correspond to verbs, so we identify what a class does. Do not focus on how a class does its job. And this is one of those rare instances where I use an exclamation point. So forget about how for now. You just focus on what an object does. Does anybody know why? That's a very important rule. It's because there are infinite hows. There are an infinite number of ways a job can get done. There's unlimited possibilities. So if you have a discussion about how, that discussion can last forever because there are unlimited possibilities. Identify information data that the class needs to carry out its task and eliminate redundant classes, similar or synonymous nouns. And the final rule is multiplicity corresponds to collections. Remember I used this example of vertex and vertices. You wouldn't use vertices as a class name. You would use something like vertex collection, the vertex collection class. Okay, so we're gonna finish this next time, next week. Are there any questions or comments about identifying objects? So next week I'm going to give you an in-class exercise where you have to identify objects.